To motivate the idea of solving an equation or an inequality by graphing, we're going to look at this example involving the hare and the tortoise. As we perhaps recall from the story, the tortoise is slow and steady, and the hare has these intervals of rest followed by intervals of a greater speed than the tortoise. Intervals of rest, again, where the function is like a constant function, and then intervals of a greater rate of change than the tortoise. And as is true in the fable, here we can see that, in fact, slow and steady wins the race, as the tortoise at the very end of the race is ahead. We're looking at this example because it's actually easier to answer these questions when there's a context than it is when we're looking at an abstract equation or inequality. So we want to do this easy example and then see what connections we can make later when we see an abstract example of an equation or an inequality that we want to solve from a graph. So the first question asks, at what times are the hare and the tortoise the same distance from the start of the race? So let's go ahead and find those times. It looks like every time the graphs cross each other, the two are the same distance from the start of the race. And we are going to estimate these. It looks like 0. Right here we have about 6, and then 12. And here it looks like that would be about 18. Then we have 24. So we would list all of these times at 0, 6, 12, 18, and 24 minutes after the start of the race. Notice that we really only gave values from the x-axis. We did not give ordered pairs, even though the graph we're looking at has ordered pairs, and the points that we identified were also ordered pairs, right? We didn't answer this with, for example, 6, comma, 0.5, which would be the y-coordinate of that ordered pair. The reason we didn't is because we were asked about the times, we weren't asked about the distances. But we're going to keep that in mind when we go to the abstract example as well. So for the next question, we are asked, over what time intervals is the hare ahead of the tortoise? For that, we want not just single values, but whole intervals where the hare's graph is above the graph of the tortoise. Ahead of, we're going to go with above. So that's going to be this interval here. And this interval here, and again, because we're only asking about times, we really need to project those down to the time axis. So I'm going to mark this interval here from 6 to 12 minutes, and this interval here also from 18 to 24 minutes. So we'll say from 6 to 12 minutes and from 18 to 24 minutes. All right. So all of the things that we just did in this example, we're going to also do when we're solving an abstract equation or inequality based on a graph, but it's not as obvious as it is in this case how to find our answer. Take, for example, this equation and inequality. The first is an equation. We see it has an equal sign. The second is an inequality. We can see it has a greater than or equal to sign. In both cases, we're going to start by considering just y equals the left-hand side of the equation. So that gives us y equals negative 3x plus 1. And think about what that graph would look like. For our first pass through, the graphs are already drawn for us, so I will just call our attention to that graph right here. and y equals the right-hand side of the equation, y equals x minus 3. We will skip the details of drawing these graphs and just call our attention to those two graphs in our grid. If we're looking for the solution to an equation, we want to identify the intersection point. The intersection point is right here, but note that it has an x and a y coordinate. This is at 1, -2. So, thinking about what we did in our hare and tortoise example, we only gave values for time because the question was about time. In this case, if we look at our original equation, we notice that it's only asking us about x. We made up y. We introduced a y variable in order to solve it graphically, but y really doesn't exist in the original equation, and therefore it doesn't exist in the original question, and we would give our answer only as the x coordinate of that intersection point. So we can see that these intersect at x equals 1, and I'm going to give x equals 1 as my answer, not the ordered pair 1, -2. Now, the -2 is relevant. If I go ahead and check this answer, I would check this by plugging in x equals 1 to the original equation. My original equation is -3 times x plus 1 equals x minus 3. I'll go ahead and plug that value 1 in for x and see what I get on both sides. I can see that I get -2 on the left and -2 on the right. Well, it's no coincidence that that is the y coordinate of the intersection point. So the y coordinate does have meaning. The y coordinate is what value both sides of the equation take on when the equation is in equilibrium, but it is not part of our solution set. So we give only the x coordinate in a situation like this where we had an equation in a single variable that we were solving by graphing. All right, so let's go on to the inequality now. For this inequality, we noted that the inequality states greater than or equal to. So the first thing I want to do when I'm solving an inequality from a graph is interpret that inequality symbol as the word above or the word below. Since this is a greater than, I'm going to interpret it as the word above. Not thinking about the or equal to part for now. That's just going to affect an endpoint value. So for the word above, that means I want the part of the graph of y equals -3x plus 1, so that's this one, that is above the graph of y equals x minus 3. I'm going to highlight that portion with a nice thick line here. And knowing that that is an arrow, because the graph keeps going, I'm going to go ahead and put an arrow on there too. The part of the graph of y equals -3x plus 1 that is above the graph of y equals x minus 3 is now drawn. But I again have to translate this to just x values. My inequality is given only in the x variable. My answer is going to consist of only x values. So I can see the intersection happens at x equals 1, and from there I can also see that it goes to the left. The portion of the line that I highlighted goes to the left. So this set that I am marking on the x-axis right now is the set that I want to translate to an interval for my solution set. I can see that that starts at -infinity because it has an arrow going off to the left. It comes up to 1, and I want to include the endpoint 1 using a closed square bracket because of the fact that this is a greater than or equal to rather than a strictly greater than. So here's my solution set, -infinity, up to positive 1 using a square bracket. So note that what these two answers have in common is that both of them express our solution sets only in x values. With the equation, we just had one answer, one value in the solution set. With our inequality, we have an infinite number of solutions because it's really every x value that's less than or equal to 1 that satisfies this inequality. Also notice that I didn't symbolically solve anything. I didn't try to get x alone on one side of the equation, right? The process of solving by graphing does not include solving symbolically as part of it. We start out with the graphs and we find the whole solution by reading the graphs.